Hello everyone. So now we will see how to solve some problems using the method of characteristic. So see the first problem. Solve the equation ux plus uy equal to 2 subject to the initial condition u at x0 equal to x square. So here a linear partial differential equation is given ux plus uy equal to 2. If you compare with the standard linear equation, we see that a is 1 here, b is 1, and c0 is 0 here, and c1 is 2. Okay, so it is a linear equation. And initial condition is given u at x0 equal to x square. What does this mean? Okay, u is a function of x and y. U at x0 means when y equal to 0. Now y equal to 0 means x-axis. So in the x-axis, the value of u is x square. So when we plot it, u takes the value on the z-axis. Okay, so here y equal to 0. So this graph is mainly in the xz plane. Okay, y equal to 0. So it is in the xz plane. In the xz plane, you have the equation is u is x square. Okay, so just like a so the figure will be like y equal to x square. The figure, how does it look? Okay, y equal to x square. So similarly, you have the figure in the z-axis. You have that figure and y equal to 0. So the initial curve lies in the xz plane. Now what we are doing in method of characteristic is we will first find the characteristic curves, which are curves which will lie in the tangent plane. If we solve the characteristic equation, you will get characteristic curves. So the curves will lie on the tangent plane. And then if you apply the initial condition, that is, you are finding the curves which starts with the initial curve. So here initial curve is a parabola. So the curves which starts with this initial curve. So from the initial curve, the characteristic curves get their information and they propagate it. So that is the geometric view. Now we will see how to do the problems. So we can directly write the characteristic equation as it was earlier discussed in the theory. Okay, because we know dx by dt is a. So here a is 1, which is a coefficient of ux. Dx by dt is 1. Dy by dt is b, which is 1, coefficient of uy. And du, here we will take u. Okay, actually u represent the z-axis. So du by dt will be 2. Here c1 is c0 is 0 and c1 is 2. So du by dt is 2. Now we will represent x, y and u as a function of t and s. T and s are any other variables. Okay. Now we will write the initial condition. Now what is the initial condition? U at x0 equal to x square. So y is 0, x-axis is there. So it takes all points on the x-axis. So we will take the initial curve t is 0. Okay, we are taking in such a way that t is 0. So x can be written as a function of t and s. So t is 0 and x of 0s is equal to s because x takes the value. It is the x-axis. Okay. Now about y is 0. So y can also be written as a function of t and s, and since it is the initial curve, t is 0 here. So y at 0s is 0. Now u takes the value x square. Again at the point we are writing the initial curve, so t is 0. So u at 0s is actually x square and x is nothing but s. At 0s, x is s. So at 0s, u is s square. So these are the characteristic equation and these are the initial curve. So first we will solve the characteristic equation to get the characteristic curves. Then we will apply the initial condition to get characteristic curves that start with the initial curve. And once we get the characteristic curves, we will apply the initial condition. So we will get curves that start with the initial curve and then we will take their union. So as s varies, we will get the union of all those characteristic curves will give you the integral surface. That is the theory. Now we'll see how we will solve this. These three are system of ordinary differential equation. So we have converted the PDE to a system of ODE. Now we are solving this. So what we are doing is, so when we integrate, so our first equation is xt of ts is equal to 1. Okay. Now I think it is visible more. So xt of ts, we are changing the variables x and y to another variable t and s. Okay. So xt is nothing but dx by dt. dx by dt is equal to 1 and dx by dt is a function of t and s. Okay. Now if you integrate it with respect to t, what we will get with so we will get x equal to t plus c. Now here c can be a function of s because we are integrating with respect to t here. Okay. So s is also a constant. So in that time we will consider s as a constant. So this constant can be a function of s. So we will get x is equal to some function of s plus t. Okay, so we have xt equal to 1 where xt is a function of t and s. We are integrating it with respect to t. Okay, so we'll get x dx is equal to dt. So we'll get x equal to t plus a constant. Instead of constant, you have to write a function of s. Now we will apply the initial condition. So this is a characteristic curve. We apply the initial condition x at 0, s is equal to s. This is the initial condition given. So we have to put t equal to 0. When t equal to 0, x is s. So we will get f1 of s equal to s. So if you substitute the value of f1 of s, we will get x of ts is equal to s plus t. So we got one characteristic curve. We got the x value of x. Okay. Now again we have the second equation, that is yt of ts is equal to 1. Again you have to integrate in the same way. So we get y is equal to t plus f2 of s. Okay, another function f2. Now we apply the initial condition y at 0s is equal to 0. So when you put t equal to 0, y is 0. This implies f2 is 0. So we'll get y of ts is equal to t. Now we have the third equation, that is ut of ts is equal to 2. Now again we integrate, so we'll get u equal to 2t plus f3 of s. Okay, now the initial condition is u at 0s is equal to s square. So when you put t equal to 0, u is s square. So this implies that f3 of s is equal to s square. So we get u of ts is equal to 2t plus s square. Hence we got a parametric representation of the integral surface. Okay, so s and t are the parameters. We get x of ts is equal to s plus t, y of ts is equal to t, u of ts is equal to 2t plus s square. So this is the parametric representation of the integral surface. Here we have the two parameters s and t. Now we will try to write the integral surface in an explicit way in terms of x and y again. Okay, so earlier it was given in x and y, the PDE was given in x and y. We converted into another plane using the variables t and s, and now again we are inverting it and writing in terms of x and y. So from first one we have x equal to s plus t, from the second one we have y equal to t, and this implies that s is equal to x minus y. Now if you put the value of s and t in u, you will get u equal to 2y plus x minus y whole square. So we got u is the integral surface. Graph of u is the integral surface. So u of xy is 2y plus x minus y whole square. So we got explicitly in terms of x and y. So earlier the PDE was in x and y. We converted in terms of s and t. First we got the parametric representation of the integral surface, and then we again inverted it. and we found the integral surface in terms of x and y. So this is u, and if we plot the graph, that is x, y, comma u, if we plot u in the z-axis, x and y we will take, so that graph will be the integral surface. Okay, so in this way we can do problems. So here this inversion was easy. Now we see that in the problem we first obtained the parametric representation, and then we inverted the transformation to get the explicit representation in x and y. Now this inversion, it is not necessary that we can always invert it like this. This inversion of the transformation from the plane TS to the plane XY is possible if and only if the Jacobian is non-zero. So in the last class we have discussed what is Jacobian. So Jacobian of dou of x comma y by dou of t comma s is non-zero, then only this inversion is possible. Now based on this we will define a condition for which a PDE will have a unique solution. So a PDE will have a unique, first order PDE will have a unique solution near the initial curve. So near the initial curve means locally. We can find a neighborhood of the initial curve in which the solution exists. And that will be possible if Jacobian is not equal to 0. And this condition is called the transversality condition. Okay, so the transversality condition says that if Jacobian is not equal to 0, then only we can find a unique solution in the neighborhood of the initial curve. Now what is Jacobian? We have discussed this in the last class. So it is defined to be dou x by dou t, dou y by dou s, minus dou x by dou s, dou y by dou t. So if you write in the determinant form, we can see that it is a, b, x naught of s, y naught of s. X naught of s is nothing but dx naught by ds. So here we are differentiating x naught, that is the initial curve. Okay, x naught is the initial curve. Dy naught of s is dy naught by ds. It is the initial curve. And here also a, b are also evaluated at the initial curve, but since in this problem a, b are constant, we can take the value as 1, 1. Okay. Now if this is not equal to 0, then only we will have a unique solution. Now what happens if this Jacobian is 0? We know that if Jacobian is 0 means this determinant is 0. We know that this determinant is 0. It means that these two vectors are linearly dependent. Now two vectors are linearly dependent if and only if one is a multiple of other. It means that AB and x naught y naught at the point at the initial value are multiples of each other. So which means that this is nothing but the projection of the characteristic curves, and this is A, B are the projection of the this is the x naught of s and y naught of s are the projection of the initial curve, and A, B are the projection of the characteristic curve. So it means that the projection of the initial curve gamma on the xy plane is tangent to the projection of the characteristic curve on that plane. So Jacobian equal to 0 geometrically, it means that the projection of the initial curve is tangent at this point to the projection of the characteristic curve. So that point here we are considering is the initial point. So that is the meaning of vanishing of Jacobian. And the third point is that we are finding when we are solving the characteristic equation, we are getting characteristic curves. Then we apply the initial condition. So the characteristic curves takes information from the initial curve. That is, initial curve says that when t equal to 0, what is the value of x? When t equal to 0, what is the value of y? When t equal to 0, what is the value of u? So it takes information from the initial curve. That is the value at point t equal to 0. And it propagates using that value. Okay, so using that value, then it continues and it goes on like that. Now, if the characteristic curve intersect an initial curve at another one more point, what happens is at that point it will have another information. Okay, that point, if it is different from the previous one, at t equal to 0, their x will be different, y will be different, u will be different. So there will be a clash. There will be a conflict. There will be a conflict. Okay, so this is not possible. So a characteristic curve should meet the initial curve only at one point. It should not meet the initial curve more than at one point. Similarly, the problem arises if the characteristic curve, if you see the projection, we are seeing projections. Okay, to study the behavior, we always see projection of the characteristic curves. So the projection of the characteristic curves, you can see that it should not intersect also. The characteristic curve should also not intersect. Then also there will be some problem. These type of things we will see in we will discuss it through problems in the next section. So the characteristic curves and initial curves we will mainly see in the projection. So to get the projection, what we have to do is, for the characteristic curves, we have to take S as constant. So if you take S constant, you will get the projection of the characteristic curves. And similarly, you will get the projection of the initial curves. So from this, we conclude that a PDE will have a unique solution in the neighborhood of the initial curve only if the Jacobian is non-zero, and this condition is called the transversality condition. So Jacobian should be not equal to 0. Then only such inversion is possible, and this PDE will have a unique solution. Otherwise, there will be some problem. Also, the points at which in some problems we will see that there will be some problems at which Jacobian vanishes. At all those points, there will be some problem. Okay. Now, if the Jacobian is 0, then also there are two conditions. Either we will have a no solution, or we will have infinite number of solutions that we will see in next problems. So you have to remember is that what you have doing is we are always checking the projection of the initial curve and the characteristic curves, and the characteristic curve should meet the initial curve only at once. Otherwise, there will be some problem. Also, the projection of the characteristic curves should not intersect more than once. Now, in the text itself, sometimes instead we will not be using about projections of, we will not use the term projection of characteristic curve. Instead of, we will simply say characteristic curves, because whenever we draw graph and all, we are talking about projections. Okay, in three-dimensional space we cannot compare it. So whenever we draw graph and see what are the characteristic curves and initial curves, it means that we are talking about projections of the characteristic curves. So sometimes we will simply use the word characteristic curves, which means that projection of characteristic curves. Okay, so we'll stop here. Thank you.